For part 4 in our discussion, we shift to this idea of the empirical rule and a related concept called Chebyshev's rule. So let's think about standard deviation again. We can think about a numerical variable having two summary measures that we've talked about. You have a mean, which tells you where the center of the data are located, and then we have a standard deviation. It tells us how spread out the data are. The mean, it's pretty intuitive for most people, just an average. It's a measure of central tendency. Where's sort of the center of a distribution of data lie? The standard deviation is a little bit more difficult for many people to understand, so we talked about a rule of thumb. If you recall, you can compare the standard deviation to the mean to get an intuitive understanding of what the standard deviation is telling us. So in general, as a rule of thumb, if a standard deviation is smaller than the mean, that suggests a narrow or distribution centered around the mean, a very small amount of spread, with the idea that if the standard deviation is 0, there's no spread, in fact. And with a larger standard deviation, as the standard deviation gets closer to the actual value of the mean, that suggests a moderate amount of spread. As the standard deviation becomes larger than the mean, that suggests a very large amount of spread. So here we have 5 sample data sets. Each of these data sets has a mean of 100. And you can see that with a standard deviation of 0, there's no spread. With a standard deviation of 5 or 10, again, compared to the mean of 100, that suggests a distribution with a pretty small amount of spread. Right? You might have, most data points are still going to be clustered around 100. With the standard deviation 85, that suggests a moderate amount of spread, because 85 is pretty close to 100. But with the standard deviation of 5,000, compared to the mean of 100, that suggests a large amount of spread. But the key point here is that if we had a different mean, then a standard deviation of 5,000, that may be a pretty small spread. So suppose the mean were 10 million. Well, standard deviation of 5,000, that's pretty small relative to the mean. So that distribution would suggest a really quite small overall spread. Yet, a standard deviation of 5,000 with respect to a mean of 100 suggests a large amount of spread. So we can use this rule of thumb of the idea of comparing the standard deviation with the mean to intuitively understand what standard deviation is telling us. Standard deviation gives us an idea of how spread out the data are, but with different means, what it means to be spread out differs. Another way of understanding standard deviation and using standard deviation is through the empirical rule. Right? The empirical rule, what it tells us is it tells us something about certain distributions. Okay? So the empirical rule, it applies only to mound-shaped symmetric data. Right? If we know a set of data, a numerical variable, it's roughly mound-shaped and symmetrical, so it looks kind of like a hump, a kind of bell, then we know that 68% of the data, roughly, lies within one standard deviation of the mean. Right? And this applies not just for samples, but you can use it for a population. If you conduct a census and you have a value of sigma, the population standard deviation, you can use the same approach. The idea is that about 68% of the data are going to lie within one standard deviation of the mean. And then the empirical rule suggests that 95% of the data are going to lie within 2 standard deviations of the mean. Be careful here, though. When we talk about rule, this is like a rule of thumb. It's sort of general characterization. About 95%, about 68% of the data. These are approximations. The other important point is that the empirical rule, again, it only applies if the data are mound-shaped and roughly symmetrical. So if your data set looks, if all the data points are kind of in one half of the histogram and there's sort of a long tail, right, you can't use the empirical rule. The empirical rule only applies when you have this general idea of what the distribution looks like, and that general idea is mound-shaped and symmetric. Having said that, that pattern in the data occurs quite often. We see a mound-shaped and symmetric set of data whenever there's a kind of signal with some noise. So for example, if you split a population into males and females and you just look at the height of males, right, nature produces sort of an average height with some noise around that average. you have a roughly mound-shaped symmetric set of data. So with height split by gender, within genders, you can use the empirical rule. What we like about the empirical rule is it helps us to understand standard deviation, and it also allows us to characterize a set of data using only two numbers, the mean and the standard deviation, and some insight about what the distribution of the data look like. So let's look at an example. Let's look at Facebook friends. So suppose you're a sociologist and you're interested in looking at friends on Facebook. You gather data of 40 students in London, and you come up with two measures. Your first measure is the amount of gray matter density in different brain regions, particularly those related to social perception and memory. And then you transform these to z-scores, so it's kind of a standardized for each individual. And then you measure the number of friends on Facebook for each friend. For our purposes now, we're going to look at the number of Facebook friends, and you want to summarize the mean number of Facebook friends for your analysis. How can you do this? Well, here's the data set, and this is a real data set. Right? This is based on an actual psychological study. In their study, they wanted to show that the more Facebook friends you have, you could look at a higher density in certain parts of the brain related to social perception. Right? So they were looking at a specific measure of association. For our purposes right now, we want to look at this value for the number of friends on Facebook. So you can see that some people have very low values, some people have a lot of friends. But we want to characterize the distribution of Facebook friends. So here is the distribution of Facebook friends in the sample. You can see it's roughly mound-shaped, or approximately. There's sort of a center part, and you kind of have this mound-shaped. And so we want to use the empirical rule to characterize, just using the mean and the standard deviation from this data set, and this knowledge of what the overall distribution looks like, we want to make some characterizations about this distribution. So we can use the empirical rule. We know in this data set that the mean number of Facebook friends is 358 roughly, and the standard deviation is 181. So first off, using the rule of thumb that you want to kind of understand spread comparing to the mean, you can say, well, okay, the standard deviation, there's some moderate amount of spread. Right? It's not completely spread out, but there's some degree of spread. The standard deviation is about half that of the mean. But we want to use the empirical rule to further understand what's going on with this set of data. So since the data are roughly mound-shaped and symmetric, we know that 68% of the data lie within one standard deviation. So we can construct an interval. So you take the mean, all right, you add and subtract the standard deviation, and we know that a good chunk of the population, or rather at least the sample, we know a good chunk of the sample, we could say people, about 68% of people have between 176 and 540 Facebook friends. Right? That characterizes 68% of people. Right? So to put another way, if you have fewer than 176 friends or more than 540 friends on Facebook, okay, you're in the minority. Right? You either have more friends than we'd expect or fewer friends. We can go further though, and we can say that 95% of the data lie within two standard deviations of the mean. So here we can say, we can construct an interval. All we're doing is we're taking the mean of x, and we're subtracting 2 times the standard deviation and adding 2 times the standard deviation. So we get this interval of negative 5.2 to 722. Right? You have to be careful with the empirical rule because negative 5.2, that doesn't make substantive sense. You can't have negative friends on Facebook. So you have to, what this interval is really telling us is that 95% of the data lie between 0 and 722 because negative values for Facebook friends doesn't make intuitive or substantive sense, rather. And so what we can, however, say is that you have, if you have more than 722 friends, you're really an unusual person because the big chunk of the population, treating this sample as some kind of population, we can characterize that most people don't have more than 722 Facebook friends. So based on just a few insights about the shape of the distribution using the mean and standard deviation, we can come to these conclusions about what proportion or what percentage of people have a certain number of Facebook friends. This is actually quite cool because you don't need that much information. All you need are two numbers, the mean and the standard deviation, and just some general knowledge about the distribution of the data, and yet you can come to these conclusions and say, most people are within this range, 95% of people are within this range, and you can make conclusions about whether certain values you'd expect to be unusual or not. So for example, for Facebook friends, if you have 900 Facebook friends, that's a pretty unusual number of Facebook friends. That's a lot. That's, 95% of people are within this range, right, of 0 to 722. And we can sort of make claims about the distribution of the data. We also see the empirical rule applied in many places because many data sets correspond roughly to a mound-shaped and symmetric distribution. Right? Again, that's a case in which you have usually some kind of signal with some kind of noise. That's when we see a mound-shaped or symmetric distribution. However, there's a problem with, or limitation with, the empirical rule. It only applies to mound-shaped data that are symmetric. Right? If you have a set of data that is mound-shaped roughly, but is asymmetric, you have to be careful. Right? The idea behind Chebyshev's rule is that it, in essence, penalizes the empirical rule. It says you can't make such broad conclusions if your data are mound-shaped, but not symmetric. So let's look at Chebyshev's rule. This is Mr. Chebyshev. He was a Russian statistician and mathematician. And what he said is that for any set of data and for any number k, where k is greater than 1, the proportion or percentage of the data that lies within k standard deviations of the mean is at least 1 minus 1 over k squared. So we'll go through an example of this. Intuitively, what all he's saying is that, okay, you think that 68% of the data lie within 1 standard deviation and 95% of the data lie within 2 standard deviations, since you're trying to apply the empirical rule. He's saying, well, be careful. If your data is mound-shaped but not symmetric, 68% is too large, 95% is too large. You're overgeneralizing. You're going to have a smaller proportion or smaller percentage of data lying within these intervals if your data are mound-shaped but asymmetric. So let's compare the empirical rule and Chebyshev's rule. So we might say, according to Chebyshev's rule, what proportion of the data lies within k standard deviations of the mean if k equals 2, if the standard deviations we're looking at are 2. What he's saying is, all we're doing is we're taking 1 minus 1 over k squared, so that's 1 minus 1/4, and we get this value of 0.75. So he's saying you might claim that 95% of the data lie within 2 standard deviations, but if your data is mound-shaped but asymmetric, in fact, you can only claim that 75%, right? He's saying at least 75% of the data will fall within 2 standard deviations of the mean. So you can think of Chebyshev's rule as a penalized version of the empirical rule. Right? It's not 95% of the data, it's less. That's the underlying point. So things to know for the empirical rule and Chebyshev's rule. We can think of the empirical rule as helping us to understand what standard deviation is telling us under the particular circumstance in which we have mound-shaped and roughly symmetric data. We can then use the empirical rule to understand what's going on. And we can characterize the distribution in terms of saying that if the distribution roughly has these properties of being mound-shaped and symmetric, we know that roughly 68% of the data lie within 1 standard deviation, and about 95% of the data lie within 2 standard deviations. However, if the data are not symmetric, then we can use Chebyshev's rule, which can be viewed as a penalty or correction, because it's not going to be 95%, it's going to be 75% that we can make claims about. And with that, we will conclude our discussion of the empirical rule and Chebyshev's rule.